Welcome to another journey through the cosmos, where tonight we'll drift among the stars of our home galaxy, exploring the gentle mysteries and soothing truths that make the Milky Way such a peaceful place to call home. I'm here to guide you through some of the most calming and beautiful facts about our galaxy, perfect for letting your mind wander as you settle into rest. There's something deeply comforting about knowing we're all passengers on this vast spiral of stars, floating together through space at unimaginable speeds, yet feeling perfectly still in our everyday lives. Tonight, we'll discover why the Milky Way earned its dreamy name, learn about the gentle dance of billions of stars, and explore the quiet corners of our galactic neighborhood, where time moves differently and space itself tells stories of ancient light. If you find these cosmic journeys helpful for relaxation, feel free to subscribe and let me know in the comments what other celestial topics help you unwind. But for now, just get comfortable, let your breathing slow, and allow yourself to be carried away by the gentle majesty of our home among the stars. The Milky Way got its name from ancient observers who saw a river of milk spilled across the night sky. Long before we understood what galaxies were, people around the world looked up and saw this soft, glowing band stretching from horizon to horizon. The ancient Greeks called it Galaxias Kyklos, meaning milky circle. The Romans named it Via Lactea, the Milky Road. Norse mythology described it as the path souls took to reach Valhalla. What they were seeing, of course, was our galaxy viewed from the inside. We live within one of the spiral arms, about 2/3 of the way out from the center, looking through the disk of billions of stars. When you gaze up at the Milky Way on a clear, dark night, you're seeing the combined light of countless distant suns, so far away they blend into that soft, cloudy glow that inspired poets and storytellers for thousands of years. This gentle river of light appears different depending on where you are on Earth and what time of year you're looking. In summer, the brightest part of the Milky Way passes overhead in many locations, showing us the direction toward the galactic center. In winter, we see the outer regions, still beautiful but more subtle, like a whispered secret written in starlight. Our galaxy is incredibly ancient, formed roughly 13.5 billion years ago, not long after the universe itself began. Think about that for a moment. The Milky Way has been spinning slowly through space for almost the entire history of everything. A cosmic elder that has witnessed the birth and death of countless generations of stars. The galaxy rotates, but so slowly that it would take our solar system about 225 million years to complete one full orbit around the center. This is called a galactic year, and in the entire history of Earth, we've completed only about 20 of these long, leisurely journeys around our galactic home. When the dinosaurs roamed the Earth, we were in a completely different part of the galaxy than we are now. This slow, steady rotation gives the Milky Way its beautiful spiral shape. The arms of the spiral aren't fixed structures like the spokes of a wheel. Instead, they're density waves, regions where stars and gas naturally collect as they orbit, creating those elegant curves that sweep outward from the center. Stars drift in and out of these arms over millions of years, like cars entering and leaving lanes of slow-moving cosmic traffic. The Milky Way contains somewhere between 100 and 400 billion stars, though the exact number remains one of astronomy's gentle mysteries. Each of these stars has its own story, its own journey through space, its own possible family of planets. Some are ancient red giants, slowly cooling as they near the end of their lives. Others are brilliant blue supergiants, burning bright and fast in their cosmic youth. Many are quiet stars like our sun, steady and reliable, perhaps warming planets where other forms of life might look up at their own night sky and wonder about the nature of their galaxy. Between the stars lies mostly empty space, but it's not completely empty. Thin clouds of gas and dust drift through the galaxy, so sparse that even the best vacuum we can create on Earth is denser. Yet these wispy materials are the raw ingredients for future stars. In the coldest, darkest regions of space, gravity slowly pulls these particles together over millions of years until they become dense enough to ignite nuclear fusion and birth new suns. The center of our galaxy holds a supermassive black hole called Sagittarius A star, with the mass of about 4 million suns compressed into a region smaller than the orbit of Mercury. Despite its incredible gravity, this black hole is so far away that it has no effect on our daily lives. It sits there quietly, 26,000 light years distant, occasionally flaring as material falls into it, but mostly just providing the gravitational anchor around which our entire galaxy slowly wheels. This distance of 26,000 light years means the light we see from the galactic center today actually left there 26,000 years ago, back when humans were just beginning to develop agriculture. The center of our galaxy exists in our past, a reminder that space and time are woven together in ways that make the universe feel both vast and intimate. Looking outward from our position in the galaxy, we can see our nearest galactic neighbors floating in the cosmic dark. The Andromeda Galaxy, our largest nearby companion, appears as a faint smudge in autumn skies, containing roughly 1 trillion stars. Despite being 2.5 million light-years away, Andromeda is actually moving toward us, though so slowly that it won't arrive for another 4.5 billion years. When it does, the two galaxies will perform a slow, graceful dance, eventually merging into a single, larger galaxy that astronomers have already nicknamed Milky Way. This future collision sounds dramatic, but it will be one of the gentlest catastrophes imaginable. The stars in both galaxies are so far apart that very few will actually collide with each other. Instead, they'll simply find new orbits in the combined galaxy, like dancers finding new partners in an incredibly slow waltz that takes billions of years to complete. Our local group of galaxies also includes dozens of smaller companions, dwarf galaxies that orbit the Milky Way like cosmic puppies following their parent. The Magellanic Clouds, visible from the southern hemisphere, are two of the most prominent. These smaller galaxies contribute their own stars and stories. Milky Way's outer regions through gentle gravitational interactions that play out over cosmic time to our cosmic neighborhood, gradually being incorporated into the Milky Way has a halo, an enormous spherical region that extends far beyond the visible disk of stars. This halo contains some of the oldest objects in the galaxy, globular clusters that formed when the universe was young. These dense collections of ancient stars orbit high above and below the galactic plane, following elliptical paths that take them far from the spiral arms where younger stars like our sun reside. Within this halo, dark matter makes up about 85% of the galaxy's total mass, though we cannot see it directly. This invisible substance reveals itself only through its gravitational effects, helping to hold the galaxy together and influencing how it rotates. Dark matter remains one of the universe's greatest mysteries, but its presence makes the galaxy feel even more mysterious and profound, like a cosmic iceberg with most of its substance hidden beneath the surface of our understanding. The disk of our galaxy is remarkably thin compared to its width. If the Milky Way were the size of a dinner plate, the disk would be only about as thick as a sheet of paper. Yet within this thin layer, an incredible diversity of stellar neighborhoods exists. Some regions are stellar nurseries where new stars are born in brilliant clusters. Others are stellar graveyards where white dwarfs and neutron stars mark the remains of stars that have completed their life cycles. Our solar system resides in what astronomers call the galactic habitable zone, a region where conditions are just right for planets like Earth to develop and maintain liquid water. Too close to the galactic center, and radiation from massive stars and the central black hole might sterilize planetary surfaces. Too far out in the galactic suburbs, and heavy elements needed for rocky planets become scarce. We live in a cosmic sweet spot, a gentle region where stars are stable and space is relatively calm. The Milky Way experiences seasons of a sort as different regions become more or less active in star formation over millions of years. Currently, we're in a relatively quiet period, with star birth proceeding at a steady but modest pace. In the past, our galaxy experienced more dramatic episodes of star formation, triggered by interactions with smaller galaxies that fell into our gravitational embrace. These galactic seasons affect the night sky in subtle ways. The patterns of star formation influence which types of stars dominate different regions, creating variations in color and brightness that sensitive instruments can detect. Some areas glow more blue from young, hot stars, while others appear redder from older, cooler stellar populations. The spiral arms themselves come and go over hundreds of millions of years, like slowly shifting weather patterns in a cosmic atmosphere. Density waves travel around the galaxy, triggering star formation as they pass through regions of gas and dust. These waves create the beautiful spiral structure we see in photographs, but individual stars don't stay locked in the arms forever. They drift in and out like leaves flowing through a slow river. Our sun has probably passed through several spiral arms during its 4.6 billion year lifetime, experiencing different stellar neighborhoods and cosmic environments. Each passage might have subtly influenced conditions in our solar system, affecting the amount of cosmic radiation reaching Earth, or the frequency of nearby supernovas that could impact our planet's climate and evolution. The magnetic field of the Milky Way creates invisible highways that guide cosmic rays on their journeys between the stars. These charged particles, accelerated by distant supernovas and other energetic events, follow the galaxy's magnetic field lines like traffic flowing along cosmic freeways. This galactic magnetic field is incredibly weak compared to a refrigerator magnet, yet it extends across thousands of light years, creating a subtle structure that influences how matter and energy move through interstellar space. This magnetic web also plays a role in star formation, helping to channel gas and dust into the dense regions where new stars can begin to shine. The field lines act like gentle guides, nudging material along paths that sometimes lead to stellar nurseries. It's a process so gradual that it takes millions of human lifetimes to see any noticeable change. Yet it's constantly reshaping the galaxy in ways too slow and vast for us to perceive directly. The Milky Way breathes in a sense, expanding and contracting slightly as waves of star formation ripple through its spiral arms. When massive stars explode as supernovas, they create bubbles of hot gas that push outward, temporarily inflating small regions of the galactic disk. These stellar winds and shock waves eventually cool and settle, allowing the galaxy to relax back into its more typical state. It's like a gentle cosmic respiration that takes place over millions of years. These breathing motions help distribute heavy elements throughout the galaxy. When stars die, they release the carbon, oxygen, iron, and other elements forged in their nuclear furnaces, enriching the interstellar medium for future generations of stars and planets. The elements in your body were created this way, in the hearts of ancient stars that lived and died long before our solar system existed. You are quite literally made of star stuff, carried here by the slow circulation of materials through galactic space. The outer edges of the Milky Way fade gradually into the emptiness between galaxies, with no clear boundary marking where our galaxy ends and intergalactic space begins. Stars become increasingly sparse as you travel outward from the spiral arms, their light growing dimmer and more scattered until finally there's nothing of light years away. It but the faint glow of distant galaxies millions is a peaceful transition, like the way ocean waves gradually fade into calm water as you move away from shore. In these outer regions, time seems to move even more slowly than in the inner galaxy. Stars are so far apart that they might not encounter another star for billions of years. Planets, if they exist out there, would experience incredibly long, cold nights with only the faintest starlight to illuminate their surfaces. Yet even in these remote areas, the gentle gravity of the galaxy still holds everything together, maintaining the connection between the loneliest stars and the bustling stellar neighborhoods closer to the center. The Milky Way contains structures called stellar streams, long ribbons of stars that trace the paths of smaller galaxies that were torn apart by our galaxy's gravity eons ago. These streams wind around the Milky Way like cosmic tinsel, marking the ancient journeys of stellar refugees that found new homes in our galactic system. Each stream tells a story of cosmic adoption, of smaller collections of stars that joined our larger family through the gentle but inexorable pull of gravity. Some of these streams are still being discovered, revealed through careful analysis of stellar motions and compositions. The stars in each stream share similar chemical signatures and velocities, like distant relatives who still carry traces of their common heritage. Following these stellar breadcrumbs backward in time, astronomers can reconstruct the history of galactic collisions and mergers that helped build the Milky Way into the majestic spiral we see today. The galaxy also contains molecular clouds, vast regions where gas molecules drift in the cold darkness between stars. These clouds are among the coldest places in the universe, just a few degrees above absolute zero, yet they're the wombs where new stars are born. Within their dark embrace, gravity slowly compresses gas and dust over millions of years until nuclear fusion finally ignites, announcing the birth of a new sun with a brilliant flash that can be seen across interstellar distances. These stellar nurseries often produce not just single stars, but entire clusters, families of suns born from the same cloud at roughly the same time. The Pleiades, visible to the naked eye as a small dipper-shaped group of stars, is one such stellar family, its members still loosely bound together by their common origin and gentle gravitational ties. Over time, most cluster members will drift apart, dispersing throughout the galaxy to pursue their individual stellar careers. The Milky Way rotates differentially, meaning stars at different distances from the center orbit at different speeds. This creates a shearing motion that gradually winds the spiral arms tighter over time, like stirring honey with a spoon. Yet somehow the spiral pattern persists, maintained by density waves that travel around the galaxy at their own pace, independent of the individual star orbits. This differential rotation also creates opportunities for stars to encounter different galactic environments during their lifetimes. A star might spend millions of years in the relative emptiness between spiral arms, then pass through a region rich in gas and dust where new stars are forming. These changing neighborhoods provide variety in the cosmic scenery, ensuring that even stars with stable orbits experience different phases of galactic life. The central bulge of the Milky Way glows with the warm light of older, redder stars that formed when the galaxy was young. This region is more densely packed with stars than our local neighborhood, creating a stellar environment where the night sky would be dramatically brighter if Earth were located there. Stars would be close enough to cast shadows, and the combined light of millions of nearby suns would create a perpetual twilight that never fades to true darkness. Yet even in this crowded stellar metropolis, the distances between individual stars remain vast by human standards. If you could somehow transport our entire solar system to the galactic center, the nearest star would still be several light years away, too distant to appear as anything more than a bright point of light. Space maintains its fundamental emptiness even in the galaxy's most densely populated regions. The Milky Way participates in the larger cosmic web, connected to other galaxies through filaments of dark matter that span hundreds of millions of light years. These invisible threads help channel matter and energy across the universe, creating the large-scale structure that gives the cosmos its web-like appearance when viewed on the grandest scales. Our galaxy flows along these cosmic currents like a boat following an ocean stream, carried by forces too vast and subtle for us to feel directly. This connection to the broader universe means the Milky Way isn't truly isolated, but part of an enormous community of galaxies that influence each other across the depths of space. Gravitational interactions with distant galaxy clusters affect our motion through space, while the expansion of the universe itself gradually stretches the distances between us and our most remote neighbors. The galaxy's rotation creates a subtle but measurable effect called frame dragging, where the spinning mass of billions of stars actually twists space-time itself. This effect is incredibly small and requires sensitive instruments to detect, but it demonstrates how the Milky Way's motion influences the very fabric of reality around it. Space and time bend slightly in response to our galaxy's rotation, creating ripples in the cosmic geometry that propagate outward at the speed of light. These gravitational waves carry information about the galaxy's mass and rotation to distant corners of the universe, announcing our presence to any civilization advanced enough to detect such subtle signals. In this way, the Milky Way broadcasts its existence across the cosmos, sharing the story of its stars and planets with the universe at large. The interstellar medium that fills the space between stars contains not just gas and dust, but also complex organic molecules, the chemical building blocks of life. These molecules form in the cold darkness of space through slow chemical reactions that take thousands of years to complete. Some of the same carbon-based compounds found in living creatures on Earth drift freely through the galaxy, suggesting that the chemistry of life might be more common than we once imagined. Radio telescopes have detected over 200 different types of molecules in interstellar space, from simple water and carbon monoxide to more complex organic compounds like methanol and ethyl alcohol. This cosmic chemistry set provides raw materials that eventually become incorporated into new planetary systems, seeding them with the molecular diversity that might one day lead to the emergence of life. The galaxy moves through space at incredible velocities that would be terrifying if we could feel them, yet we experience perfect stillness in our daily lives. Our entire solar system orbits the galactic center at roughly 515,000 miles per hour, while the Milky Way itself travels through the universe at over 1.3 million miles per hour, relative to the cosmic microwave background. Despite these tremendous speeds, the scales involved are so vast that everything feels motionless, like passengers on a cosmic cruise ship so large that its movement becomes imperceptible. This motion carries us on a journey through different regions of the universe over millions of years. The constellations our ancestors knew will gradually shift and change as our solar system follows its long orbit around the galaxy. Stars that appear close together in our night sky may actually be separated by hundreds of light years, their apparent proximity just a trick of perspective from our current cosmic vantage point. The Milky Way contains regions called stellar associations, loose groups of stars that form together but are gradually drifting apart. Unlike the tightly bound globular clusters, these associations are more like cosmic neighborhoods where stellar siblings slowly part ways over millions of years. The stars in Orion's belt, for example, aren't gravitationally bound to each other but happen to be moving through roughly the same region of space at this moment in cosmic time. These stellar associations remind us that the galaxy is in constant, gentle motion. Stars that seem permanently fixed in our constellations are actually following their own individual paths through space, some moving toward us, others away, all participating in the slow cosmic dance that gradually reshapes the night sky over timescales that dwarf human civilization. The galactic disk contains what astronomers call the thin disk and the thick disk, two overlapping populations of stars with different characteristics and histories. The thin disk, where our sun resides, contains younger stars rich in heavy elements, orbiting in relatively circular paths close to the galactic plane. The thick disk consists of older stars with more elliptical orbits that take them farther above and below the main stellar layer. This layered structure tells the story of how the Milky Way assembled itself over billions of years. The thick disk likely formed first when the galaxy was younger and more chaotic, with stars scattered into more random orbits by ancient collisions and interactions. The thin disk developed later as gas settled into a more organized rotation, allowing newer generations of stars to form in the orderly spiral pattern we see today. Between these stellar populations, space is filled with an incredibly thin soup of particles and radiation. The interstellar medium has a density so low that a volume the size of Earth's atmosphere would contain only a few pounds of material. Yet across the vast distances of the galaxy, this tenuous matter adds up to billions of times the mass of our Sun, providing the raw material for countless future stars. This sparse medium glows faintly with its own light. heated by the radiation from nearby stars and the occasional shock wave from stellar explosions. Sensitive instruments can detect this gentle radiance, mapping the temperature and composition of the gas as it flows between the stars. Some regions glow red from hydrogen, others green from oxygen, creating a subtle aurora that paints the galaxy in colors invisible to human eyes but beautiful to contemplate. The Milky Way experiences what might be called galactic weather, with regions of star formation waxing and waning over millions of years like slow-motion storms. These stellar weather patterns are driven by the galaxy's rotation and the complex interactions between gas, dust, magnetic fields, and gravity. Sometimes conditions align to trigger bursts of star formation, lighting up entire spiral arms with the brilliant blue glow of young, massive stars. Other times, the galaxy enters quieter periods where star formation slows to a gentle simmer. We currently live during one of these calmer epochs, when the Milky Way is forming new stars at a modest rate of about 1 or 2 per year. This steady pace has persisted for billions of years, suggesting that our galaxy has found a sustainable rhythm for stellar production that could continue far into the future. The outer halo of the Milky Way contains some of the most ancient objects in the known universe. Globular clusters that orbit high above the galactic disk contain stars that formed when the cosmos was less than 1 billion years old, making them among the first stellar communities to emerge after the Big Bang. These stellar time capsules preserve the chemical composition of the early universe, when heavy elements were scarce and stars formed from nearly pure hydrogen and helium. These ancient clusters follow highly elliptical orbits that take them on long journeys from the inner galaxy to the outer reaches of the halo. A typical globular cluster might take 100 million years to complete one orbit, spending most of its time in the quiet darkness far from the bustling spiral arms. During their rare passages through the galactic disk, these visitors from the early universe offer brief glimpses of cosmic history to any civilizations advanced enough to study them. The Milky Way's gravitational influence extends far beyond its visible boundaries, reaching out to capture and guide smaller galaxies across millions of light years. This gravitational embrace is gentle but inexorable, gradually drawing satellite galaxies into closer orbits while stripping away their outer stars through tidal forces. The process takes billions of years, so slow that entire civilizations could rise and fall without noticing the gradual merger taking place. Some of these cosmic adoptions are still in progress. The Sagittarius dwarf galaxy is currently being torn apart by the Milky Way's gravity, its stars scattered into long streams that wrap around our galaxy like cosmic ribbon. Other small galaxies orbit at safer distances, maintaining their independence while still feeling the gentle tug of our gravitational field. The magnetic field that pervades the galaxy creates invisible structures that channel the flow of charged particles and cosmic rays. These magnetic highways follow complex patterns, sometimes running parallel to the spiral arms, other times cutting across them at odd angles. The field strength varies from region to region, creating a three-dimensional web of magnetic force lines that guide the motion of electrically charged matter throughout galactic space. This magnetic architecture plays a crucial role in star formation, helping to support molecular clouds against gravitational collapse until conditions are just right for stellar birth. The field lines can also trigger star formation by compressing gas and dust when they collide or reconnect, creating the intricate feedback loops that regulate the galaxy's stellar production rate. Radio waves from distant pulsars travel through this magnetic maze, their signals slightly delayed and distorted by interactions with the galactic magnetic field. By studying these timing variations, astronomers can map the invisible magnetic structures that thread through interstellar space, revealing a hidden aspect of galactic architecture that influences cosmic evolution on the largest scales. The Milky Way participates in a cosmic recycling program that has been operating for billions of years. Stars are born from interstellar gas and dust, live their lives fusing lighter elements into heavier ones, then return their enriched material to space when they die. This continuous circulation gradually increases the metallicity of the galaxy, making each new generation of stars slightly richer in the heavy elements needed to form planets and support complex chemistry. This recycling process operates at different rates in different parts of the galaxy. The central regions, where stars are more densely packed, experience faster chemical evolution than the outer spiral arms. The galactic halo, populated mainly by ancient stars, retains the primitive composition of the early universe. These variations create a chemical gradient across the galaxy that tells the story of stellar evolution and element production over cosmic time. The galaxy's rotation curve, which describes how orbital velocities change with distance from the center, provided one of the first pieces of evidence for dark matter. According to the laws of gravity and the visible matter we can observe, stars in the outer regions should orbit much more slowly than they actually do. The fact that they maintain surprisingly high velocities suggests that unseen mass is providing the extra gravitational pull needed to keep them in their observed orbits. This dark matter component makes the galaxy far more massive than it appears, with the invisible matter outweighing ordinary stars and gas by a factor of 5 or 6. Yet despite its dominance, dark matter interacts so weakly with ordinary matter that we cannot detect it directly. It reveals itself only through its gravitational effects, like a cosmic ghost that shapes galactic evolution while remaining forever beyond our direct perception. The spiral density waves that create the Milky Way's elegant arm structure travel around the galaxy at a different speed than the stars themselves. This creates a traffic jam effect where stars and gas pile up as they enter the slow-moving density wave, then spread out again as they exit on the other side. The compression triggers star formation, making the spiral arms appear brighter and bluer than the regions between them. This process ensures that the spiral pattern persists even though individual stars are constantly moving in and out of the arms. It's like a wave on the ocean, where the waveform travels at one speed while the water molecules move at another. The spiral structure of the galaxy is maintained by this traveling density wave, creating the beautiful pinwheel pattern that has inspired countless photographs and artistic representations. The galactic center region harbors not just the supermassive black hole, but also some of the most extreme stellar environments in the galaxy. Stars there can orbit the central black hole at tremendous speeds, completing their orbits in just a few years, rather than the millions of years typical for stars in our neighborhood. The gravitational forces are so intense that time itself runs slightly slower there compared to our location in the outer disk. These central regions also contain some of the most massive stars known stellar giants that burn through their nuclear fuel at prodigious rates and explode as supernovas after only a few million years of life. The resulting shock waves and stellar winds create a turbulent environment where gas is heated to millions of degrees and accelerated to incredible velocities. Yet even in this cosmic maelstrom, there are pockets of relative calm where planets might form and evolve. The galaxy's diversity extends from the quiet suburbs where we live to the bustling metropolitan areas near the center, each offering different conditions for stellar and planetary development. This variety ensures that the Milky Way contains numerous distinct environments where different types of cosmic evolution can unfold. The galaxy's slow rotation and vast size mean that different regions can evolve somewhat independently, like isolated islands in a cosmic archipelago. A supernova explosion in one spiral arm has little immediate effect on star formation in another arm thousands of light years away. This allows the galaxy to support multiple ongoing experiments in stellar evolution, each proceeding at its own pace according to local conditions. Over the next few billion years, the Milky Way will continue its slow evolution, gradually consuming its remaining gas supply to form new stars, while older stars age and die. The spiral arms will continue their stately rotation, occasionally flaring with bursts of star formation when density waves compress interstellar clouds. Through it all, the galaxy will maintain its essential character as a vast community of stars, each following its own path while contributing to the larger cosmic story that unfolds across the depths of space and time. The Milky Way contains stellar streams that flow like cosmic rivers through the galaxy, marking the paths of ancient collisions and mergers that shaped our galactic home over billions of years. These streams are composed of stars that once belonged to smaller galaxies or star clusters that were gradually torn apart by our galaxy's gentle but persistent gravitational pull. The stars in each stream share similar velocities and chemical compositions, like family members scattered across vast distances but still carrying the signatures of their common origin. Following these stellar streams backward in time reveals a history of cosmic adoption, where the Milky Way gradually incorporated smaller stellar communities into its growing family. Each stream tells its own story of disruption and integration of stars that once knew different night skies before finding new homes in our galactic suburbs. Some streams wind completely around the galaxy multiple times, their member stars spread out over hundreds of thousands of light years in long, thin ribbons that astronomers are still discovering and mapping. The process of stream formation happens so gradually that it feels more like erosion than destruction. Tidal forces from the Milky Way's gravity slowly strip away the outer stars from smaller galaxies over hundreds of millions of years, while the central cores often survive as dwarf galaxies orbiting within our galactic halo. It's a gentle dismantling that preserves the individual stars while redistributing them into new patterns across the sky. Within the galactic disk, vast molecular clouds drift like cosmic icebergs through the thin interstellar medium. These clouds are among the coldest places in the universe, with temperatures just a few degrees above absolute zero, yet they serve as the nurseries where new stars are born. The largest of these clouds can contain enough material to form hundreds of thousands of stars, though the process unfolds so slowly that millions of years pass between the first gravitational stirrings and the moment when nuclear fusion finally ignites. Inside these frigid clouds, complex chemistry unfolds at an almost impossibly leisurely pace. Molecules form grain by grain on the surfaces of tiny dust particles, building up layers of ice and organic compounds over thousands of years. Water, methanol, and even amino acids drift through these stellar wombs, creating a cosmic inventory of the chemicals that might one day become incorporated into planetary systems and perhaps even living organisms. The density variations within molecular clouds create intricate structure, with some regions dense enough to eventually collapse into stars, while others remain diffuse and stable for millions of years. Magnetic fields thread through these clouds like invisible scaffolding, sometimes supporting them against gravitational collapse, and other times helping to channel material into the dense cores where stellar birth becomes inevitable. When star formation finally begins within a molecular cloud, it rarely produces just a single star. Most stars are born in clusters, stellar nurseries where dozens or hundreds of new suns ignite within a relatively small region of space. These stellar siblings share the same age and composition, having formed from the same raw materials at roughly the same time, though their individual masses can vary dramatically. The most massive stars in these clusters burn bright blue and white, exhausting their nuclear fuel in just a few million years before exploding as supernovas. Their brilliant light and stellar winds gradually disperse the remaining gas and dust from their birth cloud, effectively ending the star formation process and allowing the cluster members to begin drifting apart. Over hundreds of millions of years, most clusters dissolve completely, their member stars scattered throughout the galaxy to pursue individual careers. Some stellar clusters manage to remain gravitationally bound for much longer periods, becoming the open clusters that dot the galactic disk like scattered jewels. The Pleiades, Hyades, and other familiar star groups represent successful stellar families that have maintained their cohesion despite the disruptive influences of galactic rotation and close encounters with other cosmic objects. The chemical composition of the galaxy varies subtly from region to region, creating a metallicity gradient that reflects billions of years of stellar evolution and element production. Stars near the galactic center tend to be richer in heavy elements because that region has experienced more generations of star formation and supernova explosions. The outer regions of the galaxy contain stars with lower metallicities, preserving more primitive compositions that date back to earlier epochs of galactic history. This chemical gradient influences the types of planetary systems that can form in different galactic neighborhoods. Rocky planets like Earth require significant amounts of heavy elements to form, making them more likely to exist in the inner regions of the galaxy where stellar processing has enriched the interstellar medium. The outer regions might favor the formation of gas giant planets, though rocky worlds could still form if enough heavy elements have been transported there by stellar winds and supernovae. The Milky Way's magnetic field creates invisible highways that guide cosmic rays on their journeys between the stars. These high-energy particles, accelerated by supernova shocks and other violent processes, follow the galaxy's magnetic field lines like traffic flowing along cosmic freeways. The field itself is incredibly weak by terrestrial standards, thousands of times weaker than Earth's magnetic field, yet it extends across thousands of light years and plays crucial roles in galactic evolution. This galactic magnetic field helps regulate star formation by providing additional support against gravitational collapse in molecular clouds. It also influences how cosmic rays propagate through the galaxy, creating a more uniform distribution of high-energy particles than would exist without magnetic guidance. The field lines can reconnect and snap like cosmic rubber bands, releasing energy that heats the interstellar medium and creates regions of enhanced turbulence. The rotation of the galaxy winds up its magnetic field over time, creating complex spiral patterns that mirror but don't exactly match the spiral structure of the stellar arms. These magnetic spirals can persist for millions of years before being disrupted by stellar winds, supernova explosions, or interactions with neighboring magnetic structures. The resulting magnetic turbulence helps mix the interstellar medium, distributing heavy elements and energy throughout the galactic disk. Radio astronomers can map the galaxy's magnetic field by observing how it affects the polarization of radio waves from distant pulsars and other sources. These observations reveal a complex three-dimensional structure with magnetic loops, chimneys, and bubbles created by stellar feedback processes. Some magnetic field lines extend far above and below the galactic disk, connecting the star-forming regions to the more tenuous halo environment. The galactic halo extends far beyond the visible disk of stars, reaching out to distances of several 100,000 light-years from the galactic center. This vast spherical region contains not only the ancient globular clusters and streams of disrupted satellite galaxies, but also an enormous reservoir of hot, tenuous gas that slowly cools and falls back onto the galactic disk to fuel future episodes of star formation. This hot halo gas has temperatures of millions of degrees, heated by supernova explosions and stellar winds that drive material upward from the star-forming disk. The gas forms a kind of galactic atmosphere, a vast envelope of ionized material that mediates the exchange of matter and energy between the Milky Way and the surrounding intergalactic medium. Some of this hot gas eventually cools and condenses, raining back down onto the disk to replenish the supply of raw materials for star formation. The boundary between the Milky Way's halo and the emptiness of intergalactic space is remarkably fuzzy, with the galaxy's influence extending much farther than its visible components might suggest. Streams of gas connect our galaxy to its satellite companions, while tidal forces from nearby galaxies create subtle distortions in the outer halo that astronomers are only beginning to map and understand. Within this extended halo, the galaxy's gravitational field continues to capture and redirect small amounts of intergalactic gas, slowly adding to the Milky Way's total mass over cosmic time. This accretion process operates at an almost imperceptible rate, but over billions of years it contributes significantly to galactic growth and evolution. The galaxy breathes in cosmic material from its surroundings while exhaling processed elements through stellar winds and supernovae. The local group of galaxies, which includes the Milky Way, Andromeda, and dozens of smaller companions, occupies a relatively quiet region of the universe known as the local void. This cosmic backwater contains fewer galaxies than average, creating a more peaceful environment for galactic evolution than exists in the dense galaxy clusters found elsewhere in the universe. This relative isolation has allowed the Milky Way to evolve more gradually and steadily than galaxies in more crowded environments, where frequent interactions and mergers create more chaotic evolutionary histories. The gentle gravitational influence of distant galaxy clusters still affects our motion through space, but these forces operate over such vast distances that their effects unfold over billions of years rather than millions. The local group itself is slowly contracting under its own gravity, with the Milky Way and Andromeda galaxies approaching each other at about 250,000 miles per hour. Despite this seemingly rapid velocity, the enormous distance between the galaxies means they won't begin to interact significantly for another 4 billion years. When they do finally merge, the process will take an additional billion years to complete, unfolding so gradually that any hypothetical civilizations present at that time might barely notice the cosmic restructuring taking place around them. The interstellar medium that fills the space between stars contains not just gas and dust, but also a variety of exotic particles and phenomena that create invisible structure throughout the galaxy. Cosmic ray particles race between the stars at nearly the speed of light, their paths bent and twisted by magnetic fields into complex trajectories that can carry them across the entire galaxy before they finally interact with matter. These cosmic rays contribute to the heating and ionization of the interstellar medium, creating a subtle background of high-energy processes that influence chemical reactions and physical conditions throughout galactic space. They also provide a mechanism for mixing different regions of the galaxy, as particles accelerated by supernovae in one spiral arm can eventually reach and influence conditions in completely different parts of the galactic disk. Neutrinos, nearly massless particles that barely interact with matter, stream continuously through the galaxy from stellar cores, supernova explosions, and even more exotic sources. These ghostly particles carry information about nuclear processes deep within stars and other cosmic phenomena, creating an invisible neutrino sky that advanced civilizations might someday learn to observe and interpret. The galaxy also bathes in a faint background of gravitational waves, ripples in space-time itself created by accelerating masses throughout the universe. Most of these waves are incredibly weak, but sensitive detectors can now measure the gravitational radiation from colliding black holes and neutron stars, opening a new window on cosmic phenomena that were previously invisible to astronomical observation. The Milky Way's spiral structure creates natural laboratories where different physical processes can be studied and compared. The spiral arms themselves are regions of enhanced density where star formation proceeds more rapidly than in the quieter interarm regions. This creates a natural experiment in stellar evolution, with the arms hosting young, blue stars and active stellar nurseries, while the spaces between the arms contain older, redder stellar populations. The density waves that maintain the spiral structure travel around the galaxy at about half the speed of the stars themselves, creating a pattern that persists even as individual stars move in and out of the arms over millions of years. This differential motion ensures that the spiral structure remains visible while allowing for the complex mixing and evolution that characterizes galactic dynamics. Some regions of the galaxy experience periodic passages through spiral arms, creating cyclical variations in their stellar environments that might influence the evolution of any planetary systems in those areas. A solar system might spend tens of millions of years in the quiet interarm region, then encounter the enhanced radiation and cosmic ray flux of a spiral arm passage, potentially affecting planetary atmospheres and the development of life. The galactic disk exhibits a subtle warping at its outer edges, like a phonograph record that has been gently bent. This warp is likely caused by gravitational interactions with the Magellanic Clouds and other satellite galaxies, demonstrating how even small companions can influence the structure of much larger galactic systems. The warp extends the disk above and below the main galactic plane, creating a gentle S-curve when viewed edge-on. This warped structure affects the distribution of gas and dust in the outer galaxy, creating regions where the interstellar medium is compressed or rarefied compared to the main disk. These variations can influence star formation rates and the chemical evolution of different galactic regions, adding another layer of complexity to the already intricate processes that govern galactic evolution. The Milky Way contains multiple stellar populations that formed at different times and under different conditions throughout galactic history. The oldest stars, found primarily in the halo and thick disk, formed when the galaxy was young and chaotic, with highly elliptical orbits that reflect the turbulent conditions of early galactic assembly. These ancient stars are metal poor, having formed from gas that had been enriched by only a few generations of stellar nucleosynthesis. Younger stellar populations occupy increasingly organized orbits, with the youngest stars confined to thin disk and following nearly circular paths around the galactic center. This progression reflects the gradual settling and organization of the galactic gas supply, as turbulent motions were dissipated and the disk achieved its current state of organized rotation. The transition between different stellar populations creates subtle variations in the density and composition of stars throughout the galaxy. These gradients provide clues about how the Milky Way assembled itself from smaller components over billions of years, gradually growing from a chaotic collection of gas clouds and star clusters into the organized spiral galaxy we observe today. Even now, the galaxy continues to accrete small amounts of material from its surroundings, slowly adding to its mass and continuing the construction project that began over 13 billion years ago. High-velocity clouds of neutral hydrogen rain down onto the galactic disk from the halo, providing fresh fuel for star formation and ensuring that the galaxy's stellar production can continue for billions of years into the future. The pace of this ongoing accretion is perfectly matched to the galaxy's needs, arriving at just the right rate to sustain steady star formation without overwhelming the existing stellar populations. This cosmic coincidence suggests that galaxies naturally regulate their own growth and evolution, achieving a kind of dynamic equilibrium that can persist for most of the universe's lifetime. The Milky Way serves as our cosmic home and laboratory, a place where we can study galactic evolution and stellar processes in exquisite detail simply because we happen to live within it. Every observation we make of distant galaxies helps us understand our own, while every discovery about the Milky Way's structure and history provides insight into how galaxies form and evolve throughout the universe. From our unique vantage point within the galactic disk, we can observe stellar populations, interstellar processes, and galactic dynamics with a level of detail impossible to achieve when studying external galaxies. This inside perspective has revealed the complexity and beauty of galactic structure, showing us that our home galaxy is simultaneously a single, coherent system and a vast collection of interconnected subsystems, each operating on its own timescale while contributing to the larger galactic story. The knowledge that we are citizens of this vast stellar community, participants in a cosmic dance that has been unfolding for billions of years, provides a profound sense of connection to the universe around us. Every star we see in the night sky is a neighbor in this galactic city, every constellation a familiar landmark in our cosmic neighborhood. Every meteor shower a gentle reminder of the dynamic processes that continue to shape our galactic home. As we continue our gentle journey through the cosmic neighborhood we call home, let's drift toward some of the more mysterious and beautiful phenomena that make the Milky Way such a fascinating place to exist. The galaxy holds secrets that scientists are still uncovering, quiet processes that unfold over such vast timescales that they seem almost like whispered conversations between the stars themselves. Deep within the galactic disk, there exist regions called stellar bubbles, vast cavities carved out by the combined effects of stellar winds and supernova explosions from massive stars. These cosmic hollows can stretch for hundreds of light years across, their boundaries defined by shells of compressed gas that glow faintly with the energy of the stellar processes that created them. Within these bubbles, the interstellar medium is heated to temperatures of millions of degrees, creating pockets of space where the normal rules of stellar formation are temporarily suspended. These bubbles serve as cosmic recycling centers, mixing material from stellar interiors with the pristine gas of the interstellar medium. The hot, rarefied gas within them eventually cools and expands, carrying heavy elements produced by stellar nucleosynthesis into regions where future generations of stars will form. It's a process that operates on timescales of millions of years, so gradual that entire civilizations could rise and fall within a single bubble's lifetime without witnessing any noticeable change. The boundaries between these stellar bubbles and the cooler interstellar medium create natural laboratories where astronomers can study shock physics and plasma processes under conditions impossible to reproduce on Earth. The collision zones where expanding bubbles meet denser gas clouds can trigger new episodes of star formation, creating a feedback loop where stellar death leads directly to stellar birth in an endless cycle of cosmic renewal. Some of these bubbles connect with others to form vast networks of hot gas that extend through multiple spiral arms, creating superhighways for energy and matter transport across galactic distances. These networks help distribute the products of stellar evolution throughout the galaxy, ensuring that the chemical enrichment from one region can eventually influence star formation in completely different galactic neighborhoods. The Milky Way's rotation creates something called the galactic shear, a differential motion that gradually stretches and distorts structures within the galactic disk. This shearing motion affects everything from individual molecular clouds to vast stellar associations, slowly elongating them in the direction of galactic rotation over millions of years. The effect is so subtle that it requires careful measurements of stellar positions and velocities to detect, yet it plays a crucial role in mixing different regions of the galaxy and preventing the formation of permanent large-scale structures. This galactic shear also influences the propagation of spiral density waves, creating complex interactions between the rotating wave pattern and the underlying stellar orbits. Sometimes these interactions can amplify the spiral structure, while other times they can disrupt it, leading to the formation of spiral spurs and branches that extend outward from the main arms like cosmic tributaries. The differential rotation also creates opportunities for stellar encounters, rare events where two stars pass close enough to each other to exchange energy and alter their orbital characteristics. While such encounters are extremely infrequent in the sparse environment of the galactic disk, they do occur occasionally, sometimes ejecting stars from the galaxy entirely or sending them on highly eccentric orbits that take them far from their birthplaces. Within the galactic halo, ancient stellar streams continue to reveal the complex merger history of the Milky Way. Some of these streams are so old that their member stars have had time to spread completely around the galaxy multiple times, creating faint stellar halos that can only be detected through careful statistical analysis of stellar positions and velocities. Each stream represents a fossil remnant of galactic assembly, preserving information about conditions in the early universe when the Milky Way was still under construction. The discovery of these streams has revolutionized our understanding of how galaxies grow and evolve. Rather than forming in isolation, galaxies like the Milky Way are revealed to be the products of countless mergers and interactions with smaller systems over billions of years. Each accretion event adds not only stars, but also dark matter, gas, and angular momentum to the growing galaxy, gradually building up the complex structure we observe today. Some of the most ancient streams contain stars that formed when the universe was less than 2 billion years old, making them among the oldest objects in our galactic neighborhood. These stellar time capsules preserve the chemical signatures of the early cosmos when the first generations of stars were just beginning to enrich the universe with heavy elements. Studying their compositions provides insights into stellar nucleosynthesis and galactic chemical evolution during epochs that are otherwise inaccessible to direct observation. The Milky Way's central black hole, Sagittarius A star, occasionally flares with brief bursts of high-energy radiation as small amounts of material fall past its event horizon. These flares are remarkably gentle compared to the violent feeding frenzies observed in some other galaxies, suggesting that our central black hole is currently on a starvation diet, consuming only the occasional gas cloud or tidally disrupted star that wanders too close to its gravitational embrace. The region immediately surrounding this central black hole contains some of the most extreme stellar environments in the galaxy. Stars there orbit at velocities that would carry them across the entire solar system in a matter of hours, their paths bent into tight ellipses by the immense gravitational field. During their closest approaches to the black hole, these stars experience relativistic effects that cause time itself to run differently compared to clocks in our quiet galactic suburb. Despite the extreme conditions near the galactic center, astronomers have discovered that star formation continues even in this harsh environment. Dense molecular clouds somehow manage to collapse and form new stars despite the tidal forces and intense radiation fields that pervade the central regions. These newborn stars are often more massive than typical disk stars, burning bright and blue before exploding as supernovae after just a few million years of life. The shock waves from these central supernovae help drive material outward from the galactic center, creating a gentle galactic wind that carries processed elements into the halo and beyond. This outflow helps regulate the central black hole's feeding rate by removing potential fuel from its immediate vicinity, creating a self-regulating system that prevents the black hole from growing too rapidly or disrupting the surrounding stellar environment too dramatically. Scattered throughout the galactic disk are regions known as stellar moving groups, collections of stars that share similar velocities and chemical compositions despite being spread across large areas of sky. These groups represent the dispersed remnants of ancient star clusters that have been gradually pulled apart by galactic tidal forces over hundreds of millions of years. The member stars continue to move through space together like a cosmic convoy, following parallel paths that preserve the memory of their common origin. Some of these moving groups pass relatively close to our solar system, creating temporary enhancements in the local stellar density that can influence the dynamics of the outer solar system. The gravitational perturbations from passing stars may occasionally nudge comets in the Oort cloud onto trajectories that bring them into the inner solar system, creating meteor showers and other celestial displays that connect us directly to the larger galactic environment. The study of stellar moving groups has revealed that the solar neighborhood is far more dynamic than early astronomers realized. Rather than being a static collection of randomly distributed stars, our local galactic region is crisscrossed by streams of stars moving in coherent patterns that reflect the complex gravitational interactions and stellar formation histories that have shaped this part of the galaxy over billions of years. Within the interstellar medium, complex networks of filamentary structures connect distant molecular clouds like cosmic spiderwebs spanning hundreds of light years. These filaments are thought to channel gas flows throughout the galaxy, guiding material from regions where it's abundant to areas where star formation is actively occurring. The filaments themselves are often sites of enhanced star formation, as the converging gas flows create density enhancements that can trigger gravitational collapse. The magnetic fields that thread through these filamentary networks play crucial roles in determining their structure and evolution. Sometimes the magnetic pressure provides additional support against gravitational collapse, allowing filaments to persist for millions of years without forming stars. Other times, magnetic reconnection events can destabilize the filaments, leading to fragmentation and the formation of new stellar nurseries along their length. These filamentary networks create a kind of cosmic infrastructure that organizes star formation on galactic scales. Rather than occurring randomly throughout the disk, stellar birth is channeled along these preferred pathways, creating the complex patterns of stellar associations and star-forming regions that astronomers observe throughout the galaxy. The networks themselves evolve over time as stellar feedback processes disrupt existing filaments while gravitational instabilities create new ones. Radio observations have revealed that some of these filaments extend far above and below the galactic disk, connecting the star-forming regions to the tenuous halo environment. These vertical connections may provide pathways for material and energy exchange between different galactic components, helping to regulate the overall star formation rate and maintain the galaxy's long-term stability. The Milky Way contains several distinct kinematic populations of stars that reveal different chapters in galactic history. The oldest stars show highly random orbital motions, reflecting the chaotic conditions that prevailed when the galaxy was young and still assembling from smaller components. Intermediate age stars display more organized motion but still retain significant orbital eccentricities that carry them far above and below the main galactic plane. The youngest stellar populations are confined to the thin disk and follow nearly circular orbits that mirror the galaxy's current rotation pattern. This progression from chaos to order reflects the gradual settling of the galactic gas supply over billions of years as turbulent motions were dissipated through various friction mechanisms and the disk achieved its present state of organized rotation. These kinematic signatures provide a kind of fossil record of galactic evolution, preserving information about conditions that prevailed during different epochs, orbital characteristics of stars of galactic history. By studying them with different ages, astronomers can reconstruct the sequence of events that transform the Milky Way from a chaotic collection of gas and debris into the organized spiral galaxy we inhabit today. The transition between different kinematic populations creates subtle gradients in stellar density and composition throughout the galactic disk. These gradients influence everything from the rate of stellar encounters to the efficiency of chemical mixing, creating a complex three-dimensional structure that varies not only with distance from the galactic center, but also with height above and below the main stellar plane. Throughout the galaxy, Gravitational microlensing events occasionally occur when one star passes directly in front of another as seen from Earth, causing the background star to briefly brighten due to the focusing effect of the foreground star's gravity. These rare events provide unique opportunities to study dark objects that would otherwise be invisible, including brown dwarfs, isolated black holes, and free-floating planets that have been ejected from their parent stellar systems. The statistical properties of microlensing events reveal information about the distribution of dark matter and low-mass objects throughout the galaxy. Some surveys have detected microlensing by objects in the galactic halo, suggesting the presence of a population of dark, compact objects that might represent the remnants of the galaxy's earliest stellar generations, or even more exotic possibilities like primordial black holes formed in the early universe. These microlensing observations also provide insights into the structure of the galactic bulge, revealing details about stellar populations and kinematics that are difficult to study through direct observation due to the heavy interstellar extinction in that direction. The technique essentially uses the galaxy's own stars as natural telescopes, magnifying and revealing objects that would otherwise remain hidden in the cosmic shadows. The galaxy's rotation and the orbital motions of its stellar populations create a complex pattern of relative velocities that astronomers call the local velocity field. This field varies smoothly across the galaxy, reflecting the underlying gravitational potential and the influence of spiral density waves, stellar bars, and other large-scale structures. Small deviations from the smooth field can reveal the presence of dark matter concentrations, stellar streams, or other dynamical disturbances. Near the solar system, the local velocity field shows subtle variations that may be influenced by nearby stellar associations, molecular clouds, or even the gravitational effects of the local group of galaxies. These variations create opportunities for detecting dark matter through its gravitational effects on stellar motions, as well as for studying the detailed structure of our immediate galactic neighborhood. The measurement of stellar velocities has reached such precision that astronomers can now detect the tiny accelerations caused by the galaxy's gravitational field, providing direct observational confirmation of theoretical predictions about galactic dynamics. These measurements also reveal the presence of stellar streams and moving groups that would be difficult to detect through position measurements alone. Within the molecular clouds that serve as stellar nurseries, complex chemical processes create an inventory of organic molecules that rivals the complexity found in some biological systems. Over 200 different molecular species have been detected in interstellar space, ranging from simple diatomic molecules to complex organic compounds containing dozens of atoms. Some of these molecules are identical to those found in living organisms, suggesting that the chemical foundations of life may be widespread throughout the galaxy. The formation of these complex molecules occurs through slow chemical reactions that take place on the surfaces of microscopic dust grains over thousands of years. Ice mantles that accumulate on these grains provide protected environments where delicate molecular structures can form without being destroyed by the harsh radiation that pervades interstellar space. When these grains are eventually incorporated into forming planetary systems, they carry with them a rich chemical heritage that may contribute to the development of life. Radio telescopes have detected emission lines from molecules as complex as glycolaldehyde, a simple sugar, and even amino acids like glycine in interstellar space. These discoveries suggest that the molecular building blocks of life are naturally produced by cosmic chemistry, potentially making the emergence of life a more common phenomenon than previously thought. The galaxy may be seeded with organic molecules that provide ready-made starting materials for biological evolution wherever suitable planetary environments exist. The distribution of these complex molecules throughout the galaxy follows patterns related to star formation activity and galactic chemical evolution. Regions with recent stellar formation tend to have richer molecular inventories, while older, more evolved areas show evidence of molecular processing and destruction by stellar radiation. This creates a kind of chemical ecology that varies from region to region, potentially influencing the types of planetary systems and biological processes that can develop in different galactic neighborhoods. The Milky Way's future evolution will be shaped by several ongoing processes that operate on timescales of billions of years. The gradual consumption of the galaxy's gas supply will eventually reduce the star formation rate, leading to a slow decline in stellar birth that will continue until the interstellar medium is exhausted. This process will take tens of billions of years to complete, ensuring that star formation will continue long after our sun has evolved into a white dwarf and cooled to invisibility. The approaching merger with the Andromeda Galaxy will dramatically alter the Milky Way's structure in about 4 billion years, triggering bursts of star formation as gas clouds collide and compress throughout both galaxies. The resulting merged system, sometimes called Milkomeda, will be larger and more elliptical than either of the original galaxies, with a different pattern of stellar orbits and a restructured central region. Even after the merger, the combined galaxy will continue to evolve through interactions with other members of the local group and through the gradual expansion of the universe itself. The increasing separation between galaxy clusters will eventually isolate the local group from the rest of the cosmic web, creating an island universe that will evolve in relative isolation for the remainder of cosmic time. Despite these dramatic changes, the fundamental character of galactic evolution will remain the same. Stars will continue to form, evolve, and die, gradually enriching the interstellar medium with heavy elements and providing energy sources that could potentially support life for hundreds of billions of years into the future. The galaxy's story is far from over, with many chapters yet to be written in the slow, stately progression of cosmic time. The Milky Way serves as both our cosmic home and our window into the broader universe, a place where we can study the processes that shape all galaxies, while enjoying the unique perspective that comes from living within a galactic system. Every discovery about our home galaxy provides insights that extend far beyond the local group, helping us understand how galaxies form, evolve, and interact throughout the cosmos. From the gentle rotation of spiral arms to the violent birth and death of massive stars, from the slow accretion of satellite galaxies to the complex chemistry that unfolds in interstellar space, the Milky Way demonstrates the incredible richness and complexity that emerges from the simple interplay of gravity, electromagnetism, and the fundamental properties of matter and energy. It's a cosmic laboratory where we can observe directly the processes that astronomers can only study indirectly in distant galaxies, providing ground truth for our understanding of galactic evolution and stellar physics. As we settle deeper into rest, carried by these thoughts of cosmic time and galactic evolution, we might find comfort in knowing that we are participants in one of the universe's grandest stories. The atoms in our bodies were forged in stellar cores and distributed through space by supernovae, making us quite literally children of the galaxy. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were created through nuclear fusion in stars that lived and died long before our solar system existed. This connection between biological and cosmic evolution provides a profound sense of belonging to something much larger than ourselves. We are not separate from the galaxy, but integral parts of it, temporary arrangements of stellar material that have achieved the remarkable property of consciousness and the ability to contemplate the very cosmic processes that created us. The gentle dance of cosmic rays through our galaxy creates invisible rivers of energy that flow between the stars like ghostly currents in an ocean we cannot see. These high-energy particles, accelerated by distant supernovae and other violent stellar events, follow the galaxy's magnetic field lines as they journey across thousands of light years, carrying messages from one side of the Milky Way to the other at nearly the speed of light. Most cosmic rays are simple protons, hydrogen nuclei stripped of their electrons and flung into space with tremendous energy. Others are heavier atomic nuclei, the remnants of stellar explosions that have been accelerated to incredible velocities by shock waves propagating through the interstellar medium. As they travel, these particles interact with magnetic fields and gas clouds, their paths bent and twisted into complex trajectories that can keep them wandering through the galaxy for millions of years. The cosmic ray flux varies throughout the galaxy, creating regions of higher and lower radiation that might influence the evolution of planetary atmospheres and the development of life. Solar systems passing through areas of enhanced cosmic ray activity could experience increased mutation rates and atmospheric chemistry changes, while those in quieter regions might enjoy more stable conditions for biological evolution. These energetic particles also play important roles in heating the interstellar medium and driving chemical reactions in molecular clouds. When cosmic rays collide with gas atoms, they can break apart molecules or ionize neutral atoms, creating the complex plasma chemistry that characterizes much of interstellar space. This cosmic ray processing helps maintain the delicate balance of ionization and temperature that allows molecular clouds to persist without immediately collapsing under their own gravity. The galaxy's magnetic field that guides these cosmic rays is itself a dynamic, evolving structure that responds to stellar feedback and large-scale circulation patterns within the galactic disk. Stellar winds from massive stars can inflate magnetic bubbles that redirect cosmic ray flows, while supernova explosions can create magnetic shock fronts that accelerate new generations of high-energy particles. In the outer regions of the galactic halo, cosmic rays from the Milky Way gradually merge with the intergalactic cosmic ray background, creating a diffuse sea of energetic particles that fills the space between galaxies. This cosmic ray halo extends far beyond the visible boundaries of our galaxy, creating an invisible sphere of influence that connects us to the broader cosmic environment. The study of cosmic rays has revealed that the galaxy is far from the quiet, empty space it might appear to be in visible light. Instead, it's a dynamic, energetic environment where invisible processes constantly reshape the conditions for stellar formation and planetary evolution. The gentle rain of cosmic rays that constantly bathes our solar system serves as a reminder of these ongoing galactic processes, connecting us to events happening thousands of light years away. Within the galactic disk, vast complexes of ionized hydrogen mark regions where massive stars have recently formed. their intense ultraviolet radiation stripping electrons from surrounding gas atoms and creating glowing nebulae that can span hundreds of light years. These emission regions, invisible to the naked eye but brilliant in radio waves and infrared light, trace the galaxy's current star formation activity like cosmic cities viewed from space. The largest of these star-forming complexes can contain enough material to create thousands of new stars over the course of several million years. The process begins when density waves or stellar feedback compress molecular clouds beyond a critical threshold, triggering gravitational collapse in multiple locations simultaneously. The resulting stellar nurseries become factories of cosmic creation, transforming cold, dark gas into brilliant, hot stars that will burn for millions or billions of years. Each star-forming complex has its own character and timeline, determined by the local conditions of gas density, magnetic field strength, and the influence of nearby stellar populations. Some regions experience rapid, efficient star formation that quickly exhausts the available gas supply, while others proceed more gradually, sustaining stellar birth over tens of millions of years. The feedback from newly formed stars gradually disrupts these stellar nurseries as stellar winds and radiation pressure push away the remaining gas and dust. Eventually, the star-forming complex disperses, leaving behind a collection of young stars that slowly drift apart as they orbit the galaxy. The most massive stars in these groups will explode as supernovae within a few million years, potentially triggering new episodes of star formation in nearby molecular clouds. This cycle of stellar birth, feedback, and dispersal creates a kind of cosmic breathing that regulates the galaxy's star formation rate over long timescales. When star formation becomes too vigorous, the resulting stellar winds and supernova explosions can suppress further stellar birth by heating and dispersing the interstellar gas. When star formation slows, the gas cools and settles back into dense clouds where new stellar nurseries can form. The galaxy maintains a delicate balance between these competing processes, ensuring that star formation continues at a sustainable rate that can persist for billions of years. This self-regulation helps explain why the Milky Way has maintained its spiral structure and stellar production for most of its history, avoiding both the rapid exhaustion of gas that would end star formation and the runaway stellar birth that would quickly consume all available fuel. Throughout the galactic disk, the remnants of ancient star formation episodes can still be detected as expanding shells of hot gas and clusters of aging stars. These fossil star-forming regions provide snapshots of conditions that existed millions of years ago when different parts of the galaxy experienced their own periods of enhanced stellar creation. Some of these ancient stellar associations have dispersed so completely that their member stars are now scattered across large areas of the galaxy, identifiable only through careful analysis of their ages, chemical compositions, and orbital characteristics. Others remain partially intact as loose clusters or moving groups that continue to travel through space together, despite the disruptive effects of galactic rotation and gravitational encounters. The chemical signatures preserved in these old stellar populations reveal how the galaxy's composition has evolved over time. As successive generations of stars have processed hydrogen and helium into heavier elements, the oldest stars show evidence of formation from relatively pristine gas, while younger stars display the enrichment patterns created by billions of years of stellar nucleosynthesis and supernova explosions. This chemical evolution continues today as current episodes of star formation incorporate the heavy elements produced by previous stellar generations. The process creates a gradually increasing metallicity throughout the galaxy, though the rate of enrichment varies between different regions depending on their star formation histories and mixing timescales. The interstellar dust that pervades the galactic disk plays crucial roles in both stellar formation and galactic chemistry, serving as a catalyst for molecular formation and a repository for heavy elements produced by stellar evolution. These microscopic particles, composed primarily of silicates and carbonaceous materials, provide surfaces where gas phase atoms can meet and combine into more complex molecules. The dust grains themselves are constantly being modified by their journey through interstellar space. Stellar radiation can heat them to hundreds of degrees, causing the evaporation of volatile materials and the modification of their chemical composition. Shock waves from supernovae can shatter larger grains into smaller fragments, while accretion in dense molecular clouds can cause small particles to stick together and grow. When dust grains are incorporated into forming planetary systems, they carry with them the chemical heritage of their interstellar journey, providing the raw materials from which rocky planets and organic molecules can form. The dust in our own solar system includes particles that formed around distant stars and traveled through interstellar space for millions of years before being captured by the sun's gravity. The distribution of dust throughout the galaxy creates a complex pattern of extinction and reddening that affects how we observe distant stars and stellar populations. Dense dust lanes can completely obscure background objects in visible light, while more diffuse dust creates subtle color changes that must be corrected when measuring stellar properties and distances. Infrared observations can penetrate much of this dust extinction, revealing hidden stellar populations and star formation activity that would otherwise remain invisible. These infrared views of the galaxy show a very different picture from optical observations, highlighting the warm dust emission from star-forming regions and the cool glow from interstellar dust heated by stellar radiation. The dust also plays important roles in the energy balance of the interstellar medium, absorbing ultraviolet and optical radiation from stars and re-emitting it as infrared light. This reprocessing helps regulate the temperature of molecular clouds and influences the conditions under which star formation can occur. Submillimeter observations reveal the coldest dust components, which trace the densest and most pristine parts of molecular clouds, where the next generation of stars is likely to form. These observations provide crucial insights into the initial conditions for stellar birth and the physical processes that govern the transformation of cold gas into hot, luminous stars. The galaxy's spiral structure creates natural experiments in stellar formation and evolution, as different spiral arms experience different histories of gas accretion, stellar feedback, and chemical enrichment. The inner spiral arms, closer to the galactic center, tend to have higher metallicities and more rapid stellar formation rates, while the outer arms show evidence of more gradual, sustained star formation over longer timescales. These variations create a kind of galactic ecology, where different regions support different types of stellar populations and planetary systems. The diversity of galactic environments ensures that the Milky Way contains numerous distinct laboratories for studying stellar and planetary evolution under a wide range of physical conditions. Some spiral arms appear to be more active in forming massive stars, leading to enhanced supernova rates and more vigorous stellar feedback processes. Others seem to favor the formation of lower mass stars that burn more slowly and live longer, creating different patterns of chemical enrichment and energy injection into the interstellar medium. The spiral density waves that maintain the galaxy's structure also influence the timing and location of star formation, creating periodic episodes of enhanced stellar birth as gas clouds are compressed during their passage through the spiral arms. This process helps synchronize star formation across large regions of the galaxy, leading to the formation of stellar associations and moving groups that share common ages and compositions. Between the spiral arms, star formation proceeds more quietly and steadily, sustained by local gravitational instabilities and stellar feedback processes, rather than the large-scale compression effects associated with spiral density waves. These inter-arm regions often contain older stellar populations and provide insights into the baseline star formation processes that operate throughout the galactic disk. The interaction between spiral structure and stellar formation creates complex feedback loops that influence the galaxy's long-term evolution. Enhanced star formation in spiral arms leads to increased stellar winds and supernova explosions, which can disrupt the gas flows that maintain the spiral pattern. This self-regulation helps prevent the spiral structure from becoming too pronounced or unstable. Over very long timescales, the spiral pattern itself evolves as the galaxy ages and its gas content diminishes. Computer simulations suggest that spiral galaxies like the Milky Way may gradually transition to more elliptical configurations as their star formation rates decline and their stellar populations age. However, this transition occurs so slowly that it will take many tens of billions of years to complete. The study of our galaxy's spiral structure has revealed that it's remarkably persistent, despite the various processes that might be expected to disrupt it. The density waves that create the spiral arms are constantly being regenerated by the galaxy's rotation and the gravitational influences of stellar bars, dark matter concentrations, and satellite galaxies. This persistence suggests that spiral galaxies represent a fundamental mode of galactic organization, one that can maintain itself for most of a galaxy's lifetime under the right conditions. The Milky Way's successful maintenance of its spiral structure for billions of years indicates that the conditions in our local cosmic environment have been remarkably stable and conducive to organized galactic evolution. As we drift deeper into the contemplation of these vast galactic processes, we might find ourselves marveling at the intricate connections between the largest and smallest scales of cosmic organization. The same physical laws that govern the formation of individual stars also shape the structure of entire spiral arms, while the chemical elements produced in stellar cores eventually become incorporated into planets and living organisms. The galaxy operates as a vast recycling system, continuously transforming simple hydrogen and helium into the complex chemistry needed for planetary formation and biological evolution. Every breath we take contains oxygen atoms that were forged in the nuclear furnaces of ancient stars, while every heartbeat circulates iron that was created in supernova explosions that occurred billions of years ago. This cosmic recycling connects us intimately to the broader galactic community, making us participants in processes that span the entire history of the Milky Way. The elements in our bodies have journeyed through interstellar space, been incorporated into multiple generations of stars, and traveled across thousands of light years before finally arriving at Earth and becoming part of living organisms. The realization that we are made from processed stellar material provides a profound sense of connection to the cosmic processes that continue to shape our galaxy. We are not separate observers of galactic evolution, but integral participants in it, temporary arrangements of stellar debris that have achieved the remarkable ability to contemplate the very processes that created us. In the quiet moments before sleep, as our consciousness prepares to journey into dreams, we might imagine ourselves as cosmic citizens riding through space on our small rocky planet, members of a vast galactic community that includes billions of other stars and potentially countless other worlds. The gentle rotation of the galaxy carries us on an endless journey through space and time, a voyage that began billions of years ago and will continue long after our individual lives have ended. The Milky Way wraps around us like a cosmic blanket, its gentle light marking the boundaries of our stellar neighborhood and reminding us that we belong to something much larger and more ancient than human civilization. In its slow rotation and patient evolution, we find a rhythm that transcends the hurried pace of daily life, offering a perspective that places our brief existence within the context of cosmic time. As the galaxy continues its stately dance through the universe, carrying us along on our small blue world, we can take comfort in knowing that we are part of a story that stretches back to the very beginning of time and will continue unfolding long into the unimaginable future. The stars that shine above us tonight are fellow travelers on this cosmic journey, each following its own path while contributing to the larger pattern that makes our galaxy such a beautiful and enduring home among the stars. The rotation of our galaxy creates something astronomers call galactic fountains, where hot gas heated by stellar explosions rises far above the disk before cooling and falling back down like cosmic rain. This process takes millions of years to complete, with bubbles of superheated material climbing thousands of light years into the galactic halo before gravity eventually pulls them back toward the star-forming regions below. These fountains help regulate the galaxy's temperature and chemical composition, mixing material between the disk and halo in a slow circulation pattern that operates on timescales far longer than human civilization. The hot gas carries heavy elements produced by stellar nucleosynthesis high above the galactic plane, where they cool and condense before eventually settling back into the regions where new stars will form. The cooling process creates beautiful but invisible structures in the galactic halo, regions where hot gas gradually transitions to cooler temperatures over millions of years. Radio telescopes can detect the faint emissions from these cooling flows, revealing a complex architecture of thermal processes that helps maintain the galaxy's long-term stability. Some of the material ejected by these fountains never returns to the disk, instead escaping into the intergalactic medium and contributing to the enrichment of the space between galaxies. This galactic wind carries the products of stellar evolution beyond the Milky Way's boundaries, seeding the broader universe with heavy elements that may eventually become incorporated into other galactic systems. The galaxy's magnetic field plays crucial roles in shaping these fountains, channeling the hot gas flows along preferred directions and preventing some material from escaping entirely. The field lines act like invisible pipes, guiding the circulation of matter and energy between different parts of the galactic system in ways that help maintain its overall structure and composition. Within the galactic disk, regions of enhanced magnetic field strength create what astronomers call magnetic pressure ridges, areas where the field exerts additional support against gravitational collapse in molecular clouds. These ridges can persist for millions of years, creating long-lasting barriers that influence the patterns of star formation across large sections of spiral arms. The interaction between magnetic fields and stellar winds creates complex plasma physics phenomena that operate throughout the galaxy. When fast-moving stellar winds encounter magnetic obstacles, they can create shock waves that accelerate particles to high energies, contributing to the galaxy's cosmic ray population and creating regions of enhanced high-energy activity. These magnetic interactions also influence how supernova explosions propagate through the interstellar medium. The expanding shock waves from stellar explosions can be channeled or deflected by magnetic field lines, creating asymmetric blast patterns that help explain the complex shapes of supernova remnants observed throughout the galaxy. The galactic magnetic field itself is constantly evolving, twisted and amplified by the differential rotation of the disk, and modified by stellar feedback processes. This evolution occurs so slowly that the field maintains its basic structure for millions of years, yet fast enough to respond to major changes in stellar activity or large-scale gas flows. Deep within molecular clouds, magnetic fields help support these stellar nurseries against their own gravity, allowing them to persist for millions of years before finally collapsing to form new stars. The field lines thread through the clouds like invisible scaffolding, providing structural support that can delay or regulate the star formation process. When molecular clouds do finally collapse, the magnetic fields become concentrated along with the gas, sometimes creating powerful magnetic jets that shoot out from forming stars at incredible velocities. These jets can extend for light years, carrying away excess angular momentum and helping regulate the final masses of newly formed stars. The study of galactic magnetic fields has revealed that they play far more important roles in galactic evolution than astronomers initially realized. Rather than being passive tracers of gas motion, magnetic fields actively influence how matter moves and evolves throughout the galaxy, creating a hidden layer of organization that shapes stellar formation and galactic structure. Radio observations can map these magnetic fields by detecting the polarization of radio waves emitted by cosmic ray particles spiraling around magnetic field lines. These observations reveal complex magnetic architectures that extend throughout the galactic disk and into the halo, creating three-dimensional structures that complement the gravitational organization of the galaxy. The Milky Way contains vast reservoirs of neutral hydrogen gas that extend far beyond the visible stellar disk, creating an extended gaseous envelope that connects our galaxy to its satellite companions and the broader intergalactic environment. This neutral hydrogen, invisible to optical telescopes but detectable through radio observations, represents the raw fuel for future episodes of star formation. The distribution of this neutral gas creates a complex pattern of filaments, voids, and concentrations that reflect the influence of galactic rotation, magnetic fields, and interactions with neighboring galaxies. Some regions contain dense concentrations of neutral hydrogen that may eventually condense into molecular clouds, while others are nearly empty, swept clean by stellar winds and supernova explosions. High-velocity clouds of neutral hydrogen rain down onto the galactic disk from the halo, providing a continuous supply of fresh material to sustain star formation over cosmic time. These clouds travel at velocities that suggest they originate from interactions with satellite galaxies or from material ejected by ancient stellar explosions that is now returning to the disk. The chemistry within these neutral hydrogen regions is surprisingly complex, with trace amounts of heavier elements creating a sparse but detectable molecular inventory. These molecules form through slow chemical processes that operate over millions of years, gradually building up complex organic compounds in the cold depths of space. Radio telescopes can detect absorption lines from these molecules when they lie along the line of sight to distant radio sources, revealing the physical conditions and chemical composition of gas clouds that are otherwise invisible. These observations provide insights into the processes that prepare interstellar material for eventual incorporation into stellar and planetary systems. The neutral hydrogen also serves as a tracer of large-scale gas motions throughout the galaxy, revealing circulation patterns and streaming motions that reflect the influence of spiral density waves, stellar feedback, and gravitational interactions with satellite galaxies. These gas flows help transport material between different parts of the galaxy, contributing to chemical mixing and the regulation of star formation rates. In the outer regions of the galaxy, the neutral hydrogen disk becomes warped and distorted, creating a gently undulating structure that extends far beyond the main stellar body. This warp is likely caused by gravitational interactions with the Magellanic Clouds and other satellite galaxies, demonstrating how even small companions can influence the structure of much larger galactic systems. The warped hydrogen disk creates regions where gas densities are enhanced or depleted compared to a perfectly flat distribution, leading to variations in star formation rates and stellar populations across different parts of the outer galaxy. These variations provide natural experiments for studying how galactic structure influences stellar evolution and chemical enrichment. Throughout the galaxy, the interstellar medium contains a mixture of different temperature and density components that coexist in a complex multi-phase structure. Hot gas heated by stellar explosions creates low-density bubbles and cavities, while cold gas condenses into dense molecular clouds where star formation occurs. Between these extremes, warm, neutral, and ionized gas fills much of the volume of the galactic disk. The boundaries between these different phases are not sharp, but represent gradual transitions, where gas at different temperatures and densities mixes and exchanges energy. These phase transitions play crucial roles in regulating the overall properties of the interstellar medium and determining where and when star formation can occur. The multi-phase structure of the interstellar medium creates a kind of cosmic ecosystem where different physical processes dominate in different environments. Hot gas provides pressure support and drives large-scale circulation patterns, while cold gas serves as the raw material for stellar formation. Warm gas acts as an intermediate reservoir that can be heated or cooled depending on local conditions. This complex structure is maintained by the balance between energy input from stellar processes and energy loss through radiation and expansion. Stellar winds, supernova explosions, and ultraviolet radiation from massive stars provide the energy that keeps the interstellar medium stirred and heated, while radiative cooling and adiabatic expansion allow gas to settle into denser, cooler configurations. The study of this multi-phase interstellar medium has revealed that the galaxy is far from a simple collection of stars moving through empty space. Instead, it's a dynamic, interconnected system where stellar evolution, gas dynamics, magnetic fields, and gravitational forces all work together to create and maintain the complex structure we observe. Computer simulations of galactic evolution now include detailed models of these interstellar medium processes, showing how the interaction between stellar feedback and gas dynamics shapes the formation and evolution of spiral structure, stellar populations, and chemical abundance patterns. These simulations reveal that the interstellar medium is not just a passive reservoir of star-forming material, but an active participant in galactic evolution. The galaxy's chemical evolution proceeds through a complex interplay between stellar nucleosynthesis, stellar winds, supernova explosions, and gas mixing processes that operate on different timescales throughout the galactic disk. Different elements are produced by different types of stars and released into the interstellar medium through different mechanisms, creating complex patterns of chemical enrichment that vary across the galaxy. Oxygen and other alpha elements are produced primarily by massive stars that explode as core collapse supernova after relatively short lifetimes. These elements are released into the interstellar medium quickly after episodes of star formation, creating rapid enrichment in star-forming regions. Iron and other iron peak elements are produced mainly by type Ia supernovae, which occur on longer timescales and create more gradual enrichment patterns. The ratio of alpha elements to iron in stellar atmospheres provides a kind of cosmic clock that reveals the star formation history of different galactic regions. Stars with high alpha to iron ratios form during periods of rapid star formation, when massive stars were exploding frequently, while stars with lower ratios form during quieter periods, when type 1Wa supernovae had time to contribute their iron to the interstellar medium. These chemical signatures are preserved in stellar atmospheres for billions of years, creating a fossil record of galactic chemical evolution that can be read through spectroscopic observations of individual stars. By studying the chemical compositions of stars with different ages and orbital characteristics, astronomers can reconstruct the history of element production and mixing throughout the galaxy. The chemical evolution of the galaxy also depends on gas flows and mixing processes that transport material between different regions. Galactic rotation creates shear that can mix material across spiral arms, while stellar feedback drives vertical motions that carry process elements above and below the galactic disk. These mixing processes help create the relatively uniform chemical composition observed in stars of similar age throughout the galaxy. Recent observations have revealed subtle chemical variations between different stellar populations that provide insights into the detailed processes of galactic assembly and evolution. Some of these variations suggest that the Milky Way formed through the merger of multiple smaller systems, each with its own chemical evolution history, while others point to ongoing accretion of pristine gas from the intergalactic medium. The outer regions of the galaxy show evidence of more complex chemical evolution, with some areas displaying chemical compositions that suggest recent accretion of metal-poor gas or interactions with satellite galaxies. These observations provide clues about the ongoing assembly of the galaxy and the role of external gas accretion in sustaining star formation over cosmic time. The galaxy's chemical evolution continues today as new generations of stars form from gas that has been enriched by billions of years of stellar processing. The current interstellar medium contains roughly 2% heavy elements by mass, a dramatic increase from the nearly pristine hydrogen and helium that characterized the early universe. This ongoing enrichment ensures that planets forming today have access to the full periodic table of elements needed for complex chemistry and potentially life. Within the galactic bulge, the dense concentration of stars creates a unique environment where stellar evolution proceeds more rapidly due to the higher frequency of stellar encounters and interactions. This region contains some of the galaxy's oldest stars, formed when the Milky Way was young and still assembling from smaller components, as well as some unusual stellar populations that may have formed through different processes than the disk stars. The bulge also harbors the galaxy's central supermassive black hole, which occasionally flares with bursts of high-energy radiation as material falls across its event horizon. These flares are relatively gentle compared to the dramatic feeding frenzies observed in some other galaxies, suggesting that our central black hole is currently in a quiet phase with limited access to fuel. The region immediately surrounding the central black hole contains some of the most extreme stellar orbits in the galaxy, with stars following highly elliptical paths that bring them within a few light hours of the event horizon at closest approach. These stars experience intense tidal forces and relativistic effects during their close passages, providing natural laboratories for testing theories of gravity and stellar dynamics under extreme conditions. Despite the harsh environment near the galactic center, star formation continues even in this region, with dense molecular clouds somehow managing to collapse and form new stars despite the intense radiation fields and tidal forces. These central star-forming regions produce stars that tend to be more massive than typical disk stars, leading to enhanced supernova rates and more vigorous stellar feedback processes. The shock waves from supernovae in the galactic center region help drive a gentle wind that carries processed material outward into the galactic halo, contributing to the chemical enrichment of the halo gas and helping regulate the central black hole's accretion rate by removing potential fuel from its immediate vicinity. X-ray observations reveal hot gas flows and plasma structures throughout the central region, created by the combined effects of stellar winds, supernova explosions, and interactions with the central black hole. These high-energy phenomena create a complex, dynamic environment that influences stellar formation and evolution across the inner few thousand light-years of the galaxy. Radio observations can penetrate the dust extinction that obscures much of the galactic center in visible light, revealing details of the stellar populations, gas dynamics, and magnetic field structures that characterize this unique galactic environment. These observations show that the central region is far more active and complex than would be apparent from optical observations alone. The study of the galactic center provides insights into how supermassive black holes interact with their host galaxies and influence galactic evolution over cosmic time. The relatively quiet state of our central black hole suggests that such objects spend most of their time in low activity phases, punctuated by occasional feeding episodes when significant amounts of material fall within their gravitational reach. As we continue our gentle drift through the cosmic night, carried along by thoughts of galactic winds and stellar recycling, magnetic fields, and chemical evolution, we might find ourselves sinking deeper into the peaceful rhythm of cosmic time. The processes we've been contemplating unfold over millions and billions of years, creating a sense of vast, unhurried patience that can be deeply soothing to minds accustomed to the rapid pace of earthly concerns. The galaxy operates on timescales so vast that entire human civilizations represent barely a moment in its long history. Yet every star we see overhead is a participant in these grand cosmic processes. The gentle light reaching our eyes tonight left those distant suns years or decades or centuries ago, carrying with it the story of nuclear fusion and stellar evolution, of magnetic fields and cosmic ray acceleration, of all the invisible processes that make our galaxy such a dynamic, living system. In contemplating these cosmic processes, we connect ourselves to something far larger and more enduring than our individual lives, finding perspective and peace in the knowledge that we are part of an ancient, ongoing story that stretches back to the very beginning of time. The elements in our bodies, the energy that powers our thoughts, even the genetic information that defines our biological nature, all originated in stellar cores and have been shaped by billions of years of galactic evolution. This cosmic perspective can be deeply comforting, reminding us that we belong to something magnificent and eternal, that our brief existence is part of a larger pattern that gives meaning and context to the momentary concerns that might otherwise keep us awake. The galaxy wraps around us like a vast protective embrace, its billions of stars serving as nightlights in the cosmic darkness, gentle beacons that mark our place in the universal community of worlds. As consciousness begins to fade and dreams prepare to carry us into sleep, we might imagine ourselves floating peacefully through the galactic disk, surrounded by the soft glow of distant stars and the invisible currents of cosmic rays and magnetic fields that connect every part of our stellar neighborhood. In this cosmic cradle, rocked gently by the rotation of spiral arms and the slow breathing of stellar birth and death, we can find the deepest, most restful sleep, knowing that we are home among the stars. The gentle currents of dark matter flow invisibly through our galaxy like cosmic rivers we cannot see, yet their influence shapes everything around us. These mysterious streams make up roughly 85% of the Milky Way's total mass, creating the gravitational scaffolding that holds our entire stellar community together. Without this invisible foundation, the galaxy's spiral arms would long ago have flung themselves apart into the emptiness of space. Dark matter particles, whatever they may be, rarely interact with the ordinary matter that makes up stars and planets and ourselves. They pass through solid rock and human bodies alike as if we were made of nothing but empty space. Yet their collective gravitational pull guides the motions of entire stellar systems, bending the paths of star clusters and shaping the large-scale architecture of galactic structure. Computer simulations reveal that dark matter forms vast halos around galaxies like ours, extending far beyond the visible boundaries of stars and gas. These halos are not smooth and uniform, but contain intricate substructure, with streams and clumps and voids that create a complex three-dimensional web of gravitational influence. The visible galaxy we see in photographs represents only the bright tip of this much larger, invisible iceberg. The distribution of dark matter influences where and when stars can form throughout the galactic disk. Regions of enhanced dark matter density provide additional gravitational support that can help molecular clouds resist disruption by stellar winds and radiation pressure. Other areas, where dark matter is less concentrated, may experience more chaotic conditions that either suppress star formation entirely or trigger it through gravitational instabilities. As our solar system orbits the galaxy, we move through varying concentrations of dark matter that change over millions of years. These variations are too subtle to affect planetary orbits or the stability of our solar system, yet they represent our passage through different neighborhoods of this invisible cosmic web. In a sense, we swim through dark matter like fish moving through an ocean we cannot perceive directly. The search for dark matter continues in laboratories deep underground and in space-based detectors, yet these elusive particles remain as mysterious as ever. Some theories suggest they might occasionally interact with ordinary matter in ways so rare that billions of particles must be monitored for years before a single interaction might be detected. Other ideas propose that dark matter could be made of entirely different types of particles than anything in the standard model of physics. Whatever dark matter turns out to be, its presence reminds us that the universe contains far more than meets the eye. The bright stars and colorful nebulae that fill astronomical photographs represent only a small fraction of cosmic reality. Most of the universe consists of invisible components that reveal themselves only through their gravitational effects, creating hidden layers of organization that guide the evolution of everything we can see. This invisible majority of cosmic matter operates according to physical laws we understand, yet it remains tantalizingly beyond our direct perception. It's as if the universe is written in a language where we can read only a few scattered words while the rest of the text remains hidden from view. The dark matter that surrounds and permeates our galaxy represents perhaps the greatest mystery in modern astronomy, a puzzle that connects the smallest scales of particle physics to the largest structures in the cosmos. In the spaces between stars, quantum fluctuations create tiny ripples in the fabric of space-time itself. Brief tremors so small that they exist at the very edge of what physics considers real. These quantum whispers arise from the fundamental uncertainty that characterizes reality at its deepest level, where particles can appear and disappear in fleeting moments too brief to measure directly. Even in the near-perfect vacuum of interstellar space, this quantum activity continues ceaselessly. Virtual particles pop into existence in perfectly matched pairs, borrowing energy from the universe's quantum credit system, before annihilating each other and returning that energy in timeframes so short that the universe's accounting books never quite balance. It's as if space itself is alive with invisible activity, a constant background of creation and destruction happening everywhere at once. These quantum fluctuations may seem like mere curiosities of theoretical physics, yet they have profound implications for our understanding of reality. They suggest that what we think of as empty space is actually a seething foam of quantum activity, with particles and antiparticles constantly appearing and disappearing like bubbles forming and bursting on the surface of an invisible ocean. Our journey through the gentle mysteries of the Milky Way draws to a close, like starlight fading into the soft embrace of dawn. We've drifted together through spiral arms and stellar nurseries, past ancient globular clusters, and into the quiet depths where dark matter flows like invisible rivers through space. Each fact we've explored tonight has been a small window into the vast, patient story our galaxy has been writing across billions of years. Tonight we've discovered that we live not just on a planet, but within a cosmic community of unimaginable beauty and complexity. Every breath connects us to stellar furnaces that burned long before Earth existed. Every heartbeat carries iron forged in ancient supernovae. Every thought arises from atoms that have journeyed across thousands of light years to become part of us. The Milky Way holds us gently in its gravitational embrace, carrying us on a journey that began before life itself and will continue long after our brief moment has passed. In its slow rotation and endless patience, we find a rhythm that transcends our earthly concerns, offering perspective that can quiet even the most restless mind. As you settle into sleep, let yourself be cradled by these cosmic truths. You are not separate from the galaxy, but woven into its very fabric, a temporary arrangement of stellar material that has achieved the remarkable gift of consciousness. The stars that shine above are your distant family members, fellow travelers on this ancient voyage through space and time. Sweet dreams, cosmic wanderer, and may your rest be as peaceful as the gentle dance of stars across the endless night.